In this lecture, we will discuss first excitons in quantum wells and see how they differ from excitons in bulk. And then we will go on to some discussion of a relationship between the optical constants in a material. Excitons were first discovered in materials like copper oxide, and they were observed at low temperature. However, when it came to looking at optical absorption when optical absorption was studied in gallium arsenide, gallium aluminum arsenide quantum wells, it was found that even at room temperature one could see features. If you plot alpha against energy, this is for a gallium arsenide, Al-gas quantum well with wells with LZ, it was found even at room temperature one could find LZ is the width of the well in which electrons are located. This well is made of gallium arsenide and the barrier is Al-gas. And the well width, well height is delta EC, conduction band discontinuity, and the well height in the valence band is delta EV. Now it was found that looking at the optical absorption in such layers, one found that even at room temperature one could get very sharp optical absorption peaks. This is for a well width of say 40 nanometers. Suppose you reduced the well width, then obviously from arguments of electron in a potential well, according to Schrödinger's formulation, the energy splittings increase and the optical absorption becomes of this type. For LZ, 21 nanometers. And these peaks correspond to n equal to 1, 2, 3, etc. In the expression for energy. And if you reduce the well size even further, this is pushed up a little. This is for LZ is equal to 14 nanometers. And we find then that as expected, E is inversely proportional to the well width LZ squared, as in the case of the Schrödinger formulation of an electron in a potential well. So this work was first done by Gossard et al. At Bell Labs. And it showed that even at room temperature, excitonic features are available, are observable. Now, the reason behind this is easy to understand, that in bulk gallium arsenide, the excitonic energies are of the order of 4.4 milli-electron volts. and the thermal broadening due to optical photons is also of the order of 4 MeV. Remember, Kt at room temperature is 26 MeV. So these excitons, if you look at this conduction band, the excitonic energy, fundamental excitonic energy is lower by only 4.4 MeV. Okay. The electrons can be easily broken up thermally, the electrons and holes, and you get a free electron and a free hole. And as a result, at room temperature, the excitons are not stable. Okay. It was found that through experiments, measurement of the excitonic binding energy, that as the well size Lz varied, say, from between 50 to 250 nanometers, from the bulk value of 4.5, the excitonic binding energy increased rather significantly and decreased. As the well size increases, we tend to gradually get back to the bulk value. And the binding energy for an exciton in a well of with 50 nanometers can be as much as 9.5 MeV. So this explains why this is particularly for a quantum well gallium arsenide, aluminium 0.3, gallium 0.7 arsenide composition. This composition determines the height of the potential wells. So this explains why excitons are stable even at room temperature in quantum wells. Now, if you look at the actual physical arrangement, if you take a multi-quantum well, this is the valence band, the conduction band, and this is Lz, this is L barrier, width of the barrier. So the wells are gallium arsenide, as I've mentioned before, and the barriers are algas. So we have a series of levels corresponding to L equal to 1, 2, 3 in the conduction band. In the valence band, we have a series of levels corresponding to first the heavy holes, and since the light holes have lower effective mass, then LH is equal to 1, L equal to 1, L equal to 2. So we have a series of ladders corresponding to light holes and heavy holes in the valence band and electrons in the conduction band. And this is the conduction band discontinuity, and this is the valence band discontinuity. These depend upon the composition, aluminium. As the aluminium composition increases, these delta C's and ECs and EVs increase. So when light is incident on such a quantum well, we can get excitations from the heavy hole band, the first excitation, the lowest energy will be from the HH L equal to 1 band to the electron L equal to 1 band. Okay. Then the next one will be from the LH equal to 1 to the electron L equal to 1. There are selection rules that say that delta N equal to 0 will give you the strongest permitted absorption. So from L equal to 2 level here to L equal to 2 level there, you will get a series of absorptions corresponding to transitions between discrete levels in the valence band and discrete levels in the conduction band. Where do excitons come in? Now, excitons give rise to absorption slightly below the band gap. And excitons, as you know, are bound electron hole pairs. Here, the electron wave function can be shown by something like this, and the whole wave function can be shown by something like this. Okay. So, remember, these are weakly bound excitons. So, the extent of the well width Lz may in many cases be less than the dimension of the diameter of the exciton, right? So, instead, in the bulk, suppose the exciton diameter could be something like this. Typically in gallium arsenide, the exciton diameter could be something like 300 angstroms. But since the electron and wave functions are being confined by the wells, in the quantum well, the electron wave function will be confined and it will take a sort of a pancake shape. This can be calculated mathematically, but physically this is what is going to happen. So there is going to be strong confinement of the electrons and holes in these quantum wells, and as a result, of this strong overlap between the electron and hole wave functions in a narrow region. Here, the electron wave and hole wave functions are spread out over a large region. Here, it's confined. Therefore, that is the physical basis for the increase in the binding energy. If the electron is localized and the hole is also localized, then the exciton binding energy increases much more strongly, and hence these exciton effects are observable at room temperature. This is really a two-dimensional system. This is in the sense that the layers go perpendicular to the line of the paper. So this is a two-dimensional system, and in such a system, which are quantum wells, the excitonic binding energy is equal to approximately twice the excitonic binding energy in the bulk minus 3 EP, the phonon energy. And the absorption coefficient in such a two-dimensional system has been calculated, and it turns out to be given by this expression. Where N2D, the two-dimensional density of states, is mr squared over pi h cross squared. This is what is two-dimensional density of states, which we'll derive later on. FCV is the oscillator strength, H cross omega is the energy, this is NR is the refractive index, and AP is the factor due to polarization dependence of the matrix element which governs the transition probability from the valence band to the conduction band, and this is equal to half for gallium arsenide. And H cross omega is the energy of the photon. Notice that this shows that the absorption coefficient is 1 by Lz. The energies are proportional to 1 by Lz squared, but the absorption coefficient is proportional to 1 by Lz. So you would think that by having smaller and smaller value of Lz, alpha would increase, right? But this is not so. There is an optimum value of Lz, because as Lz becomes smaller and smaller, the electron wave functions cannot be confined within that potential well. It spreads out, it decays into, for example, if you make this extremely small, then the wave function tunnels into the potential barrier. For example, if you have a very narrow potential well, then the electron wave function obviously will go like that, and only a small portion is within the barrier. Okay. So there is an optimum well size depending upon the material. For gallium arsenide, the optimum well size for strong absorption due to excitons is Lz is of the order of 50 angstroms. For indium gallium arsenide wells, Lz is of the order of 80 angstroms. So 5 nanometers and 8 nanometers. And we mentioned that the other system, apart from the gas-algas system that I've talked about, is the in-gas indium phosphide system. In which the barrier is made out of indium phosphide and the well is made out of indium gallium arsenide, which lattice matches at particular value of x is equal to 0.47. So in this case, Lz, the optimum barrier width, is a little larger, 80 angstroms. The other difference between this system and the gas-algas system is here the well is a alloy, is a ternary alloy. The barrier is a binary compound. Okay. In the case of the gas-algas system, which I showed here, okay, the well is the binary and the barrier is a ternary alloy. Okay. So the scattering of electrons is different in a binary and in a ternary system. Right. So this explains why excitonic effects are important at room temperature in quantum wells. Now, from the application point of view, what is important is what happens to absorption in a quantum well when an electric field is applied? Suppose this is Eg. The lowest absorption energy is when H cross omega causes the transition from the first heavy hole band to the lowest electron band. Okay. Now, if you apply an electric field, we've discussed what happens with electric field. We have Stark effects coming in, and with an electric field, the energy bands are tilted. That is the conduction band, and the electric field is in this direction. Right, the electric field is in this direction. Right. This is electron energies, right? So this is EC, this is EV, and what happens? Originally, the electron wave function was there, and the whole wave function was there. The peaks are located at the same point in space. X is space. Okay. Now, in this case, the whole wave function will be displaced towards the left. So the whole wave function is positive charge is displaced towards the left, whereas the electron wave function is displaced towards the right, and as a result there is reduced overlap between the electron and whole wave functions. Therefore, there is a lower alpha, and there is also reduction in photoluminescence efficiency. Photoluminescence occurs when an electron is transferred from the conduction band to the valence band. Lower overlap means there's lower probability of recombination, and so you have reduced PL. If you look into this and calculate what are the energies involved, this is EPH, the energy going from the valence band to the conduction band. In this case, EPH is equal to EE plus EH plus EGW minus E exciton. Where EE and EH are the electron and hole binding energies. This is the excitonic energy, and with an electric field 10 to the power 4 to 10 to the power 5 volts per centimeter, we have a change in delta EPH of the order of about 20 MeV, which is much larger than for bulk semiconductors. Okay, that is the really the band gap in the well. Okay. This is the band gap in the well, okay, EGW. So with an electric field, what EGW and EX, there are small changes, but EE and EH, there is reduction in the subband energies. So this accounts for the rather large change, 20 MeV, whereas we've seen that in the bulk this is of the order of a few MeV. Okay. So the result is, now if you look at the optical absorption as a function of the electric field, we find quite remarkable changes. At 298K, when you have no field, okay, this is H cross omega, the photon energy, (1.43 to 1.49 for gallium arsenide). Without any electric field, we find that the optical absorption is of this type. 0 voltage, five, 10, 15, and 20 volts applied. So there is a strong shift, alpha shifts to lower energies with electric field, and this is known as the quantum confined Stark effect. It is essentially due to the fact that, due to the Stark effect, these energies EE and EH are reduced, and as a result the absorption shifts towards lower energies. This is very important. I'll go into this in the case of light modulators. This is a very fast effect because there are no carrier injections involved. It is just an electric field effect. Suppose you have a light source operating at this wavelength. Okay. So the optical absorption is very low. Without any electric field, light is transmitted. But if you apply the electric field, optical absorption becomes large and the light is cut off. So with the application of electric field, the light is cut off, and so you can switch the light on and off using this quantum confined Stark effect. So this is an important type of modulator, which I'll discuss in detail when I come to discussion of devices. And broadly speaking, this shows that the phenomena of optical absorption in quantum wells is different from that in bulk. One has much higher excitonic effects because the excitonic binding energies are larger. There are discrete transitions from valence band to conduction band depending upon the band structure. And later on I will also show that if you have wells or superlattices with strain built in, then the basic band structure can also be changed, and that would change the optical absorption as well as the luminescent efficiencies. So this brings to an end this particular discussion about different methods of optical absorption. So let me just bring out the relation between optical constants that are involved when you have basically the relations between n, k on the one hand and epsilon and epsilon prime. The real and imaginary parts of the dielectric constant are related to the refractive index and the extinction coefficient, right? And this is also related to alpha. This is in the nature of a revision. It is just to refresh your minds. If you have an electric field, if you have a wave, velocity of propagation of a plane wave of frequency mu, we know that E is equal to E0 exponential I 2 pi nu t minus x by v. Now, suppose we say the wave is propagating through a medium with complex refractive index NC, which is equal to n minus ik. N is the refractive in the real part, the refractive index, and k is the imaginary part, which is the extinction coefficient. We know the velocity of light in a medium is given by c over nc, complex refractive index, and so from these we can write 1 by v is equal to n by c minus ik by c. Now we can write this expression as E is equal to E0 exponential I 2 pi nu t exponential minus I 2 pi x nu n by c into exponential minus 2 pi nu kx by c. Separating into real and imaginary parts, n minus ik. So if we have incident power of intensity P0, transmitted power Px, Px over P0 is, for a medium with conductivity sigma, is sigma E squared x over sigma E squared 0, and this is exponential minus 4 pi nu kx by c. We had 2 pi nu here. This is proportional to E squared. Okay, so you have 4 pi nu kx by c. And this is, from definition, we know this is also equal to exponential minus alpha x. Okay, if this is x, Px is equal to P0 into e to the power minus alpha x. So therefore we get a relation between alpha. Alpha is 4 pi nu k by c. So this is the extinction coefficient, which is imaginary part of the refractive index, and this is the measured absorption coefficient. And you see they're linearly related. This is just 4 pi nu by c, frequency and the wavelength.
So extension coefficient equal to imaginary part of?
NC is equal to n minus ik. Okay. This is the real and this is the imaginary part. Now, if we look at the index of refraction, what I want to do next is try and find what n and k are in terms of epsilon and sigma, the dielectric constant and the conductivity of a medium. So we start with Maxwell's equations. In a medium with permeability mu, dielectric constant epsilon, and conductivity sigma. From this we can derive a wave equation using the four Maxwell's equations. d2e dx squared is mu by c squared 4 pi sigma dE by dt plus mu epsilon over c squared. So it's a relation between spatial variation and the temporal variation. And writing E is equal to E0 exponential I 2 pi nu t minus x by v, and substituting into this, we substitute d2e dx squared and d2e dt squared d dt, we find this expression comes to 2 pi nu squared over v squared I 2 pi nu by c squared 4 pi sigma minus mu epsilon by c squared 2 pi nu squared. Straightforward substitution of this into that. Or if we simplify this, we calculate the 2 pi nu. It's 1 by v squared is equal to mu epsilon, this term, over c squared minus I mu 4 pi sigma by 2 pi nu c squared. Let me just rewrite that. 1 by v squared is equal to mu epsilon. In semiconductors, mu is equal to 1, so this is simplified to 1 by v squared is equal to epsilon by c squared minus I 2 sigma by nu c squared. Earlier we had 1 by v squared is equal to nc squared by c squared. This is n squared over c squared minus I twice nk over c squared minus k squared by c squared. So we can equate the real and imaginary parts and we get a very well-known expression. N squared minus k squared is equal to epsilon, and n k is equal to sigma by nu. Extremely well-known expression relating the real and imaginary part of the refractive index to the dielectric constant and the conductivity. So we can solve for n and k, and I leave it to you as a simple exercise. You can get solving, you get n squared is equal to half epsilon 1 plus twice sigma by mu epsilon squared to the power half plus 1, and k squared is one plus twice sigma by mu epsilon minus 1. So this is the real part, this is the imaginary part, and you can see that when sigma, take case when the material is completely insulating, non-lossy, is a perfect insulator, what you have, if this goes, this term goes, okay, you have n squared, there is a 2 sigma squared, this you take the root, etc., you get a 2 sigma, this cancels, so n squared is equal to epsilon, right, or n is equal to root e, and k tends to 0. Okay. Extinction coefficient, so k tends to 0 is that material is fully transparent, no absorption. So this these relations are important because if you measure the sigma, the conductivity of a material, you can calculate the extinction coefficient. If you know sigma and E, you can calculate N and K. This expression also is quite well known, that the refractive index, square of the refractive index is equal to the dielectric constant, the real part of the dielectric constant. We can take other special cases when sigma is very large. If you have a case of a metal, you take sigma is very large, and then you can expand this, and you can work it out and see what the values of n and k come to in those cases. But obviously, if you go back to look at this expression, n squared minus k squared, so here, for example, if right here, if you put k equal to 0, n squared is epsilon, okay, and if k is equal to 0, then obviously sigma is equal to 0, okay, so this equation must be satisfied, okay, straight off. As a postscript, in semiconductors, it was found that there is a thing called Moss law, or Moss rule. It's an empirical rule. N4th into Eg is some constant, 77. That means that Eg is 77 by N4th. Okay. So what does it mean? That if the refractive index is large, band gap is small. Okay. And if the refractive index is small, the band gap is large. That means for large band gap materials, the refractive index is small. That's the case for diamond, boron nitride, etc. Okay. Or zinc sulfide. This is valid for, that means for N going from 2.34 to 4.58, Eg goes from about 2.56 to 0.175. So if you have a material like indium antimonide having a low band gap, N squared, that is epsilon is almost equal to N squared, so that would be quite large, of the order of 20. Okay. And if the band gap is quite large, then the refractive index is small. This is also important in the case of a material like we've been talking about heterojunctions, gallium arsenide, gallium aluminum arsenide. We find that we'll go back to this later, that aluminum arsenide, gallium arsenide, the refractive index of aluminum arsenide is lower than that of gallium arsenide, and the band gap is, on the other hand, if you plot the band gap, 1.4, and this is of the order of about 2.2. Okay, so you get some variation like that. Okay, so this is important in optical confinement. If we have a material this is gallium arsenide, this is Al gas. Just as in the case of optical fiber, if light is confined in this region, the light will be subject to total internal reflection, and it will be confined in this region, the region with higher refractive index. Okay. N well is usually larger than N of the barrier. Right, I will stop here today, and I'll go into a brief discussion of Kramer-Kronig relation and then get into applications of optical absorption in semiconductor devices.